Okay, so if we want to keep this guy on the inside of this spinning ride, then we want to make sure that the frictional force between this guy and the wall, right, the frictional force is going to be utilizing at least the minimum of static friction. Does that make sense? Right? Because we want him to stay there, so we want to make sure that's there. So when I do my force diagram, or here's my drawing, when I do my force diagram, some of the forces are obviously equal to ma sub c. Some of the forces in the y, 0 if he stays there. So we have Fn equals mv squared over r, and we have Fg to Ff. Ff is mu F sub n. So now I can sub, and I get mg is equal to mu mv squared over r. M's cancel, and I get, wait, are we supposed to do it in omega? We are, right? Yeah. So instead of v squared over r, what I should have done is I should have said mu omega squared times r. So then that allows for omega, which will be the square root of g over mu r, something like that.
Wait, does that cancel out the m?
Good question. Which mu do we use? They give us 4. I'm going to concentrate on, or that one, the minimums. This is the minimum for kinetic. That's the minimum for static. What do we want this person to do?
Find the minimum angular velocity necessary, or you want the friction to be as big as possible?
No, I just want the friction to be big enough to keep them there, right? See, like, the big, like, the smaller friction is, the less sticky the wall is, the faster I have to spin them. Because if mu is smaller, then Fn has to be bigger. Right? Does that make sense? Because I still have to match gravity. No matter what I do, I have to match gravity. So if, and so that means I'm dealing with a constant on the demand. So if I decrease the mu, then I have to increase Fn, which means I have to spin it faster. And then the We're supposed to find what? Sorry?
You just need to find angular velocity.
Oh, just find angular velocity? Okay.